Hi Math 30-1s, welcome to lesson 7 with permutations and combinations. What we're going to talk about today is something called Pascal's triangle, and what it really relates to is the expansion of any binomial. So you can see up here at the top with the title x plus y to the exponent of n. So that n is going to be any exponent. So, a binomial squared or cubed, anything along those lines. And we're going to see that when we expand those binomials, there are patterns, okay, that exist with the numerical coefficients, which are the numbers in front of the variables for each term, and also patterns that exist with the variables themselves. Okay, so in this first section, it says we're going to talk about x plus y to the exponent of n, and only for values or exponents that are be less than or equal to 4. So in the first example here, they want me to expand or write in simplest form x plus y to the exponent of 0. So anything to the exponent of 0 has a value of 1. Okay, that's pretty simple, pretty straightforward. When I take the binomial x plus y to the exponent of 1, okay, to simplify that, well, that's just x plus y, okay? Nothing more than that. It gets a little more complicated in B here, so they want me to expand x plus y squared. Now, x plus y squared, okay, when I write that out, okay, what it means is x plus y times x plus y, right? That goes back to your math 10. When I expand that, making sure I multiply each term in each binomial by every other term in the other binomial, okay, you end up with x squared plus 2xy plus y squared, okay? So nothing too crazy yet. When I expand x plus y cubed, okay, so that's x plus y 3 times, isn't it? What that really is it's going to be an x plus y plus x plus y squared, which is what I just determined the product of up above. So that's x squared plus 2xy plus y squared. So I'm going to take the x in the first binomial and distribute it to the x squared, the 2xy, and the y squared, and then take the y in the first binomial and distribute it as well to the x squared, 2xy, and y squared in the second bracket. Now, when I do that and I collect my like terms, okay, I will end up with x cubed plus 3x squared y plus 3xy squared, and finally y cubed. And then when I move to the expansion now of x plus y to the exponent of 4, okay, what that's going to be is x plus y times x plus y cubed, right, which are 3 more x plus y's. And the product there, just from the previous step, is x cubed plus 3x squared y plus 3xy squared plus y cubed. So again, taking the first x in the binomial and distributing it to every term in the second bracket, and then taking the y in the first binomial and distributing it to each term in the second bracket, collecting my like terms, I will end up with x to the exponent of 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed, okay, plus y to the exponent of 4. Now, in this unit, or this chapter, these sections here, okay, the point is not that I want you to be able to expand a binomial with any exponent by writing it out, okay, and distributing over and over and over again, okay, because the size of the exponents we're going to be dealing with are going to get quite large. What I want to be able to do with you today and in the next lesson is see the patterns that are existing here, and then we'll be able to quickly expand any binomial no matter the size of the exponent. Okay, so I'm just going to be copying down my products here from up above. Okay, and when I do that, you'll see that they have x plus y to the exponent of 0 done for me. That's 1. X plus y to the exponent of 1 is just x plus y. X plus y squared was x squared plus 2xy plus y squared. Then I had for x plus y cubed, x cubed plus 3x squared y plus 3xy squared plus y cubed. And then finally for x plus y to the exponent of 4, x to the exponent of 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed, and then finally plus y to the exponent of 4. Okay, so now we start to take a look at the relationships here between these binomials we expanded. Okay, and you'll see D, E, and F, they're asking us something different to notice about the patterns. So the first one says, state the number of terms in the expansion. So when I take a look at x plus y squared, okay, which is up here, how many terms do I end up with? 1, 2, and 3. So 3 terms. When I expand x plus y cubed, okay, up here, there are 1, 2, 3, 4 terms, okay? So the pattern that we're starting to see is that when I expand a binomial, there's always going to be one more term than the exponent of the binomial I'm expanding. So therefore, if I'm going to expand x plus y to the exponent of 4, there should be 5 terms. And when I go to something much larger, x plus y to the exponent of 20, there will be 21 terms, okay? So that's our new rule that we are going to use moving forward, that when I expand a binomial with a particular exponent, there's always one more term than the exponent attached to the binomial. In E, they're asking for the sum of the exponents in each term, okay? So when they're asking for the sum of the exponents in each term, okay, what they're looking for, okay, is the following. Sorry, for some reason this kind of got lost there, so I'm just going to fill that in again, okay? So the sum of the exponents. So when I go to x plus y squared, the sum of the exponents is what they're talking about in each term. So in the first term, the sum of the exponents is just 2. There's just a 2 there. The sum of the exponents in the second term would be 1 plus 1. That is also 2. And for the third term, it's obviously 2. So the sum of the exponents in each term was 2. For x plus y cubed, okay, the sum of the exponents. Again, the first term is 3. In the second term, the 2, which is squared on the x, and the 1 attached to the y, that's 3. In the next term, 1 and 2 is 3, and again, the last term is 3. So what we're seeing now is that the sum of the exponents in each term is equal to the exponent of the binomial that we're expanding. So therefore, okay, this should be 4, and it is if you look up above, the sum of the exponents in each term is 4, and therefore carrying that over to x plus y to the exponent of 20, the sum of the exponents in each term will also be 20. Okay, so 2 little rules, okay, or patterns that we have now noticed expanding these binomials. In F, it says complete the following arrays which show the coefficients of the terms in each of the expansion. Now remember, the coefficients, sometimes referred to as the numerical coefficients, are the numbers that exist in front of the variables. So when I take a look at x plus y to the exponent of 0 up above, okay, the number there is just a 1. So I write that there. For x plus y to the exponent of 1, okay, there's a 1 in front of the x and a 1 in front of the y. So 1 and 1, those are the numerical coefficients. For x plus y squared, 1 x squared, 2 xy, 1 y squared. Okay, so that's the pattern we're following here. X plus y cubed, there's a 1 in front of the x cubed, 3 in front of the x squared y, 3 in front of the xy squared, and then a 1 in front of the y cubed. And for x plus y to the exponent of 4, you'll see there's a 1 in front of the x to the exponent of 4, 4 in front of the x cubed y, 6 in front of the x squared y squared, 4 again in front of xy cubed, and then 1 in front of the y to the exponent of 4. So I take that same array and I move to the right where they ask me just to write it as a triangular array. So the same numbers, okay, I'm just setting it up so it forms a triangular pattern as opposed to just writing all of the numbers over top of each other, okay? So the same values, I'm just copying them. And there we go. It says explore the patterns in the triangular array and complete the next row in the triangle. So what you're going to notice, or hopefully what you notice, okay, is the following. That when I want to find, for example, this number 3, I get it by adding this 1 and this 2. They come together to add that value. Okay. Similarly, if I want this, for example, this number 4, I would have added this 3 and this 1. They give me that value. So if I follow that pattern, here's what happens. With Pascal's triangle, okay, which is what we're learning here, there's always a 1 on the outside of the triangle, okay? So each row begins and ends with a coefficient or a value of 1. Then I would get 5 here, okay, by adding 1 and 4. Then I add the 4 and the 6 to get 10. 6 and 4 again is 10, and 4 and 1 is 5. So there's the next row in that triangle. Okay, so let's turn the page and see what we're going to talk about next. So the properties of expanding any binomial x plus y to the exponent of n. And this time we're going to go one more, and we're going to take a look at binomials where the exponent on the outside is anything from 0 to 5. Okay, and that's what we have here. X plus y to the exponent of 0, x plus y to the exponent of 1, x plus y squared, x plus y cubed, x plus y to the exponent of 4, and x plus y now to the exponent of 5. Using the above expansions, complete the following. Now this is based on the title where it says there are n, okay, is our exponent. So when n is my exponent, doesn't matter, okay, you pick a number in your head, how many terms are there going to be? Well, there's always going to be n plus 1 terms. So we learned this on the last page, right? For example, when my exponent is 0, there's 1 term. When my exponent is 1, there are 2 terms. When the exponent is 2, there are 3 terms, okay, so on and so forth. So whatever the exponent is of the binomial I'm expanding, there's always going to be 1 more term. Next, it says the sum of the exponents of x and y in each term. So again, if I refer to x plus y cubed, the sum of the exponents of each term, well, 3. In the next one, 2 and 1, that's 3. 1 and 2, that's 3, and then 3 again. So the sum of the exponents in each term is equal to the exponent of the binomial I'm expanding. So the sum of the exponents in each term would be whatever n is. Okay, so that's kind of another little thing that we're going to need to use moving forward here. The exponents of x are doing what? Well, what do they mean by that? Well, if you take a look at, and this time I'll refer to x to the exponent of 4, look what happens to the x is x to the 4, 3, 2, 1, and then, well, really there is an x to the exponent of 0 here, but anything to the exponent of 0 is 1, so we don't write it. But that means the values of x, or the exponents of x, are decreasing, okay? So the exponents of x decrease term by term from n to 0. Then they ask about y. Well, let's take a look at the next one, x plus y to the exponent of 5. What happens? Well, there's a y to the exponent of 0 here, okay, again, which is 1, but then y to the exponent of 1, y squared, y cubed, y to the exponent of 4, and then y to the 5th. So that means the exponents of y are increasing, okay, or they increase term by term. Okay, so x's decrease term to term, and y's increase term to term. And the coefficients form what kind of pattern? Well, it's going to be a symmetrical pattern. Okay, so we're just going to fill that in, and then I'll show you what I mean. If I take a look again at x plus y to the exponent of 5, look at the coefficients: 1, 5, 10, and then again 10, 5, and 1. Okay, so that's a symmetrical pattern, and that's what you're going to notice for the expansion of any binomial. Those numerical coefficients are going to form that type of symmetrical pattern. So now taking a look at Pascal's triangle, it says the coefficients in the above expansion can be put in a triangular array known as Pascal's triangle, named after Blaise Pascal, who developed applications of the triangle in the 17th century. Use the patterns to complete the next 3 rows of Pascal's triangle. So like I had mentioned on the previous page, each row begins with 1 on the outside, and then to find any term, I add the 2 diagonal values above it. Okay, so that 2 and 1 give me a 3, or for example, this 6 and this 4 will give me this 10. So if I follow that pattern, falling in the next row, I will have a 6 here, okay, by adding this 1 and this 5. Then 15, 20, 15, 6, and 1. Okay, the next row, 1 and 1 on the outside, and then 7, 21, 35, 35, 21, 7 and 1, and then finally at the bottom here, okay, 1, and then we'll just go across 8, 28, 56, 70, 56, 28, 8, and 1. Okay, so you have completed, along with me, the next 3 rows in that triangle. So how does this help us? Well, in B it says complete the following expansions. Now, I want to expand x plus y to the exponent of 6. Well, what we have to remember is that these rows of Pascal's triangle come from this. This number 1 at the top is really the expansion of x plus y to the exponent of 0. The next row, the 1 and the 1, those are the numerical coefficients for x plus y to the exponent of 1. The next row, okay, these are the numerical coefficients for x plus y squared, okay? So on and so forth. So if they're asking me to expand x plus y to the exponent of 6, I just keep going down, and this is what you're going to see. So there's squared, 3, 4, 5. This row right here where I'm drawing the red arrow is x plus y to the exponent of 6, okay? Which is, in essence, the 1, 2, 3, 4, 5, 6. It's actually the 7th row, isn't it? So the 7th row in Pascal's triangle gives me the numerical coefficients when I expand the binomial x plus y to the exponent of 6. So this is how it works. The number 1 there, okay, is the one that is in front of the x to the exponent of 6. The next number 6, okay, is going to be the next numerical coefficient, and now I follow the pattern about x's and y's. The x's go down by 1, and the y's now start increasing. Okay, so y to the 1. Plus, then I use the 15. So 15, the x goes down by 1, the y increases by 1. Then the 20, so plus 20, the x goes down by 1, the y increases by 1. Okay, then another 15, so 15, x squared, y to the 4th, then plus the 6, this will be x, y to the exponent of 5, and then finally that last one, so plus 1, and then no more x's, or x to the exponent of 0, and y to the exponent of 6. And there you go. That's what would happen, or that would what the end expression would be when I expand x plus y to the exponent of 6. So therefore, we should be able to easily do x plus y to the exponent of 7 now, which is, okay, the next row down, there's x plus y to the exponent of 7, which is, again, the 8th row. So in that 8th row, you can see all the coefficients there. So the first one will be a 1, x to the exponent of 7, okay, plus then 7, x to the 6th y, plus 21, x to the exponent of 5, y squared, plus 35, okay, x to the exponent of 4, y cubed, plus another 35, x cubed, y to the exponent of 4, plus 21 now, x squared, y to the exponent of 5, plus 7, x, y to the exponent of 6, and then finally plus 1, y to the exponent of 7. So we've quickly expanded that binomial. So when I was writing out the row numbers there by the expansion of the binomials in that diagram up above, this is why. Okay, they want us to see this relationship. It says, which row of Pascal's triangle is equivalent to the coefficients of the terms in this expansion? So what they're really asking you is, when I have x plus y to the exponent of 6, which row is that? Well, that's actually row 7. When I have x plus y to the exponent of 7, that's actually row 8. And when I have x plus y to the exponent of 12, that's actually row what? 13. So the row number is always one more than the exponent. So therefore, if I have x plus y to the exponent of n, that would simply be row, whatever n is, plus 1. Okay, and there we go. So Pascal's triangle and combinations. So what you're going to see here is that I can actually write the value of each number in Pascal's triangle as a combination. And what I mean is this. This number 1, okay, can be written as 0, choose 0. Well, why? Because this is the number 1, but it's actually x plus y to the exponent of 0. Okay, in the next row, okay, I have a 1 and a 1, which I'm going to write as 1, choose 0, 1, choose 1. Okay, that comes from x plus y to the exponent of 1. Okay, and that pattern continues the whole way down. So what they asked me to do now is state the first 3 terms in the 8th row. Okay, so they've done the first 7. Here's row 8. I'm filling that in. The first 3 terms would be a 1, a 7, and 21. Again, that 7, for example, comes from adding 1 and 6, doesn't it? Okay, and the 6 and the 15 give me that 21. Okay, they want it in numerical form and in combination notation. So this is going to be 7, choose 0. This will be 7, choose 1, and 7, choose 2. Okay, that's how I write those. State the last 3 terms. Well, because Pascal's triangle is symmetrical, I know that I'm going to end in 21, 7, and 1. And for combinations, okay, we know that that is going to be 7, choose 5, 7, choose 6, and 7, choose 7, right? So it's going to end in 7, choose 7. So this would have been 7, choose 6, and this would have been 7, choose 5. So when they say, use Pascal's triangle now, this is part C, to write the following as a single combination, it's the same pattern, right? They're asking me to add 4 choose 2 and 4 choose 3. Well, that's going to give me 5 choose 3. Then they ask me to add 6 choose 0 and 6 choose 1. Well, that's going to give me 7 choose 1. Okay, and then just a generic case where I don't know the specific values of n and r, but if I have n choose r plus n choose r plus 1, okay, that's going to give me the next row down. So that would be n plus 1 choose r plus 1. Okay, so you know that third example that I just did is important, but if you understand the two that I did previously, the one in the blue and the red, then you'll be okay with in terms of understanding Pascal's triangle with combinations. Now, what we're going to take a look at here is investigating what we call three sums that are equal to 2 to the exponent of n. So this expression of 2 to the exponent of n becomes very important moving forward. Okay? So it says complete the table for the sum of the numbers in each of the first 6 rows of Pascal's triangle. So row number 1, okay, that's what we're talking about here, row number 1. Well, in row number 1, remember, this is x plus y to the exponent of 0. Okay, that's the binomial we're expanding in row 1. What is the sum of the numbers in row 1? Well, the sum of the numbers, this is 1, so the sum of the numbers is 1. How do you write the number 1 as a power with a base of 2? Well, it's actually 2 to the exponent of 0. Okay. When I go to row number 2, okay, well, remember row number 2 is actually x plus y to the exponent of 1, which ends up being x plus y. Well, the sum of the numbers, there's a 1 in front of the x and a 1 in front of the y. So if I add 1 and 1, I get 2, and that is actually 2 to the exponent of 1. Okay, so what you're going to see here is that this number here, okay, is equivalent to the exponent on the outside, isn't it? Okay, moving along, the third row, okay, well, this is going to actually just be x plus y what? Squared. Okay, so remember that gave us x squared plus 2xy plus y squared. Well, if I add those numbers, the 1, the 2, and the 1, okay, that's going to be 4. Well, that's 2 squared, isn't it? Okay, equivalent to this exponent out here. So continuing on with that pattern, okay, for row 4, well, that would be x plus y cubed. So 2 cubed would be 8. Okay, the next row, okay, this is row number 5. Well, that is going to be 2 to the exponent of 4 because it's x plus y to the exponent of 4, and 2 to the exponent of 4 is 16. Okay, the sixth row, it's actually going to be 2 to the exponent of 5 because it's x plus y to the exponent of 5. So that's going to be 32. And then just as some generic cases, if I have an n, well, it's actually going to be 2 to the exponent of 1 less than the n value. Okay, and the same basically goes for the next one. If it's n plus 1, 1 less than n plus 1 is just n. Okay, so going back up here now, it says the sum of the numbers in the n plus 1 row of Pascal's triangle is actually 2 to the n, 1 less than the row number. So that's the relationship they're trying to show you here. Part 2 says look at row 5 in Pascal's triangle, okay, which is 4 choose 0. Okay, here's the fifth row, right? 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay, refer to part 1 and express this as a power of 2. Well, what it's really going to be is 2 to the exponent of 4, isn't it? Because this number is 1 less than the row number, but it's also the number that we're starting to choose from. So if I take a look at that, okay, in the next one, okay, I start with 6 choose 0, so this is going to be 2 to the exponent of 6, okay? 1 less than the row number. Okay, makes sense. And in the last one here, okay, I start with n choose 0, so this is simply going to be 2 to the exponent of n. Okay, and you'll see how we use all these moving forward, I promise. Okay. Next, okay, what are we considering now? Well, now we're going to compare the value of n, which is the exponent on the outside, and the sum of the coefficients, okay? Not necessarily the row number, but just the value of n. So they start in the first one with n being 1, okay, which is right here, x plus y to the exponent of 1. The sum of the coefficients there, again, remember, 1 and 1, that's going to be 2, so that's 2 to the exponent of 1. Then I move to where n is 2. This is where n is 2, the sum of the coefficients, 1, 2, and 1, that's 4, and that's 2 squared. So this time you're seeing the exponent on 2 is the same as the value of n. Okay, then the next one we're going to have where n is 3. Here's where the exponent or value of n is 3. The sum of the coefficients, 1, 3, 3, and 1. Okay, that is going to be 8, which is 2 cubed. Okay, moving along, n is 4. Okay, add up the coefficients there. You're going to find that it is 16, 2 to the exponent of 4. Okay, and then when n is 5, this is going to be 32 because that is equivalent to 2 to the exponent of 5. Okay, so right here, the sum of the coefficients in the expansion of x plus y to the exponent of n is just 2 to the n. Okay, so when I know what the exponent is of the binomial I'm expanding, it's 2 to the value of that exponent, and that's what the sum of those numbers are. So these three sums are extremely, extremely important, and we need to know all three of them or be aware of them. The sum of the numbers in the n plus 1 row is 2 to the n. When it's written out in terms of combinations, n choose 0 plus n choose 1, etc., all the way up to n choose n, it's 2 to the n. And the sum of the coefficients in the expansion of x plus y to the exponent of n is 2 to the n. So you can see that the sums here, three sums that all equal 2 to the n, but one of them is based on the row number. One of them is based on, okay, the values that we are choosing from, and the other one is based on, okay, the value of the exponent attached to the binomial. Okay, so all three of them, we have to know those relationships, okay, give us a value of 2 to the exponent of n. So let's practice some questions here based on those principles. Determine the sum of the numbers in the 10th row. Okay, well, if I'm in the 10th row, I know that my exponent is actually going to be 9, so it's going to be 2 to the exponent of 9. That's going to be the value of the coefficients in that row, which is going to be 512. Remember, the exponent is going to be 1 less than the row number. Okay. The sum of the coefficients in the expansion of m plus n to the exponent of 12. Well, this time I actually know the exponent attached to the binomial, so it's simply 2 to the exponent of 12. Okay, so 2 to the exponent of 12, it gives me 4,096. Okay. Part C deals with writing out the values in terms of combinations. So you'll notice here that I start with 15 choose 0 and it goes all the way up to 15 choose 15, okay? And they even have the etc there, meaning they have every term in between. So I've got the whole row there. So when I'm going 15 choose 0, 15 choose 1, that is just going to be 2 to the exponent of 15, okay? Which again, 2 to the exponent of 15 is going to be 32,768. Okay. In the second question, okay, you have to be very careful here because I start at 6 choose 0, add 6 choose 1, add 6 choose 2, and again they go dot, 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 but they end at 6 choose 5. They don't go all the way up to 6 choose 6. That's what they should have, all the way up to 6 choose 6. So this calculation will be 2 to the exponent of 6. That would be the whole row, but minus 6 choose 6 because that's the one I'm missing. So 2 to the exponent of 6 is 64. 6 choose 1 is 1. Okay, so the value in the second one is just 63. Okay, 1 less than you would think, but that's because of that little tricky part at the end there. Okay. What we move on to now, you guys, is what we call pathway questions. Now, we've seen these before, and we've solved them in the past using permutations and repetitions. So this question here, as it says, recall from the following problem in lesson 3, we have seen before. So remember with these questions, I'm traveling from A to B. I always have to move closer. And the way we did the calculation is I said, okay, count up the moves on the outside. 1, 2, 3, 4, 5. So 5 total movements. Okay, so that would be 5 factorial. And of those 5 total movements, I have 3 repeated movements to the right and 2 repeated movements down. So 5 factorial over 3 factorial, 2 factorial is 10, okay, which is the exact same calculation they've shown us here. And we've done that already. Another way to solve these problems, or some of these problems, okay, I should say, is to use Pascal's triangle. So what they've taken is the grid from up above and duplicated it twice here. Now, here's A, where they start up above, and there's B. They just turned the grid kind of diagonally, okay? And you'll see why in a second. So what I'm going to do is I'm going to relabel over here A and B, okay? It's the same diagram. Now, what I'm going to do is I'm going to use Pascal's triangle, or overlay Pascal's triangle on this grid, and you're going to see how we can solve the problem this way. So we know on the outside of Pascal's triangle, okay, we always have the numbers 1. Okay, so that's the first thing I do. I put 1 all the way down the sides like so. And now I use the pattern that we created or saw, okay, with Pascal's triangle to find the values at the points which are missing. So 1 and 1, that's 2, okay? Then I keep going. 1 and 2, that gives me 3, okay? And I keep going with this pattern. 2 and 1, that gives me 3. So I keep going with this diagonal pattern. 3 and 3, that gives me 6. The 3 and this 1 gives me 4. And what do you know? 6 and 4 gives me 10. Okay, the same answer we got when we used permutations with repetitions. So to answer the questions now, we've kind of worked ahead, or I did this in a little bit different order, but it asks me now here, how does F compare to C and D? Well, if I take a look at that, C plus D gives me F. So I would simply just say F is equal to C plus D. It says, how does H compare to E and F? Well, you could just say again that H is equal to E plus F. And then finally, how does I compare to F and G? Well, again, similar in the sense that we say I is equal to F plus G, okay? C says use the relationship in B to complete the second diagram, which we have done, and compare your answers with Catherine's answer, and we did that as well, okay? I get 10 as the number of roots possible in both scenarios. Now that we have two different ways of basically calculating pathway problems, okay, you're going to see that we can use both scenarios or both calculation methods a lot of the time, but there are scenarios where we can only use one versus the other, and that's what we're going to take a look at below, okay, in class example 2 and 3. Before we get there, okay, we want to take a look at this, that remember when we were talking about Pascal's triangle, I can write it like this as 1 or 0, choose 0, okay? That's x plus y to the exponent of 0. The next row, okay, remember we have a 1 and a 1. Okay, that's 1, choose 0, or 1, choose 1, which comes from x plus y to the exponent of 1. Okay, the next row, okay, would be 1, 2, and 1. And those are your numerical coefficients, again, coming from 2, choose 0, 2, choose 1, and 2, choose 2, which comes from the expansion of x plus y squared. So maybe I'll write those in here, okay, to show you where these come from. So this is x plus y to the exponent of 0. Okay, this represents the numerical coefficients of x plus y to the exponent of 1. Okay, and this represents the numerical coefficients for x plus y squared. Okay, and that pattern continues the whole way down as I overlay those arrays onto the grid. Okay, so what they're asking here is notice that 10, okay, which is here at the bottom of the first one, is equivalent to 5, choose 3, okay? So 10 is the numerical value, 5, choose 3 is the same value, but written in combination notation, okay? So here we go, class example 2 and 3. So before I start the questions, I'll tell you why, okay, or in which scenario we can use both methods to determine the end result, and in which ones we're a little bit limited. So if you take a look at class example 2 versus class example 3, you'll notice that in class example 2, I basically have two perfect grids, okay? This first one I'll outline in blue, okay? And then I have another perfect grid, okay, right here, attached, okay, right at the corner. So when I have two perfect grids, okay, squares, rectangles, doesn't matter, and there is no overlap of the two grids, or there are no pieces or squares missing from either grid, I can use both methods to calculate the end result, Pascal's triangle and permutations with repetitions. In class example 3, if you look down there right now, you'll notice that it looks like I have two grids that are maybe overlapped a little bit, or one grid where potentially I'm missing a square in this top right corner and maybe a couple squares down here in the left corner. In that case, I cannot use permutations with repetitions. I can only use Pascal's triangle. So I want you to make a note of that just by class example 2 and 3 here, that when I have two perfect grids that are connected at a corner, no overlap, no missing corners or intersections, anything along those lines, I can use both methods. But for class example 3, where I have missing portions of a grid or I have grids that are overlapped, you cannot use permutations with repetitions. You have to use Pascal's triangle, okay? So I'm going to do the questions now and obviously talk my way through them so that you understand how I'm doing it. but just have those notes there so that when you go to your assignments or we're getting ready for quizzes and tests, you're aware of the limitations, okay, of permutations with repetitions. Now, in the first one, class example 2, it says a supervisor of the city bus department is determining how many routes there are from the bus station to the concert hall. Determine the number of routes possible if the bus must always move closer to the concert hall. So again, there's that little caveat in the question. We always have to make a movement closer to our end destination. So I outlined the bus station grid in blue, so I'll do that calculation in blue first. So again, to get from the bus station to that first corner, there are 1, 2, 3, 4, 5, 6, 7 total movements. And of those 7 total movements, there are 3 repeated movements to the right and 4 repeated movements down. Okay? Now you've gotten to this intersection, then you would say, and then, which in math means multiply, and then I have to do the red grid, which there are 1, 2, 3, 4 total movements. And of those 4 total movements, I have 2 repeated movements to the right and 2 repeated movements down. Okay, so there's my calculation. Do each of those perms with repetitions individually and then multiply the values together. So 7 factorial over 3 factorial, 4 factorial is going to be a value of 35. To that, I multiply the calculation of 4 factorial, 2 factorial, 2 factorial, which is a value of 6. Okay, and those two, okay, 35 times 6 is 210. Okay, so there is what we are after. Okay, 210. So I actually did B first. Now I'll do A, Pascal's triangle. Okay, so remember 210 is the answer that we are after. So I'm just going to get rid of this so that I have a clear grid to work with. Now, Pascal's triangle, here's how it works. Remember, my bus station is where I'm starting. So what I do is I put 1s on the outside of my grid, okay, going to the right and going down, just like Pascal's triangle. Now, if you have to turn or tilt your head to do this because we're adding diagonally, then that's fine. If you don't, then okay, that's great. So here's what happens, right? Remember, I add diagonally. So 1 and 1, that gives me 2. Then 2 and 1, that gives me 3. Then 3 and 1, that gives me 4. Okay? Then I keep going. 1 and 2, that gives me 3. 3 and 3 gives me 6. 6 and 4, that gives me 10. And I carry on. 1 and 3 is 4. 4 and 6 is 10. 10 and 10, that is 20. Okay, and then I keep going. So 1 and 4, that's 5. 5 and 10 is 15. 15 and 20, that's 35. Okay, so I've gotten to that first corner. I'm at the end of my first grid. Now it's like I start Pascal's triangle again, except instead of starting with a number 1, I start with the number 35. So 35 goes across, and 35 goes down the grid. Now, the reason for it being 35 and no more is that there's no more ways for me to get here than there are to get up here. Okay, there's no additional routes. The number of ways I can get to that intersection is the same number of ways I can get to the bottom. Okay, so I just carry on with my pattern like I did before. So 35 and 35, that is 70. 70 and 35 is 110. This 35 down here and this 70 is also 110, and 110 and 110 is 200. Oh, sorry, 105 is what I should have there, right? 105. I made a mistake there, so I'll just erase these. Okay, so 70 and 35 should be 105 and 105, and that takes me to 210. Okay, which was the same calculation we got when we used perms with repetitions. Okay, so apologize for that little slip there, but we did end up with the same number at the end. Now in class example 3, okay, remember, I cannot use perms with repetitions, and I'll explain that in part B, which is what they ask for, but let's use Pascal's triangle to determine the number of routes from the train station to the football station. So again, okay, 1s go across, okay, and 1s go down, okay? Now I add, okay, diagonally. So again, 1 and 1, remember that's 2. 2 and 1 is 3. 3 and 1 is 4. Now this is where I get a little stuck because we're missing this portion here, but there's like a 0 here because I can't get there, right? There's nothing there to get to. So that number 4 just carries to this corner because there's the same number of ways to get here as there is to get here. Okay, so that 4 just slides across, or we add it in at the next point there to its right. Then I go back and I keep adding. So 2 and 1, that is 3. 3 and 3 is 6. 6 and 4 is 10. 10 and 4 is 14. Okay, and the pattern continues 4, 10, 20, 34. Okay, and again, keep going. 1 and 4, that's 5. That's 15, that's 35, that's 69. Now this 15 here, same number of ways to get here. So 15, and now 15 and 35. Okay, that is going to be 50, and then 50 and 69 is 119. And there's your result. Okay, the number of pathways or ways to get from the train station to the football station. Now it says explain why the permutations 9 factorial over 4 factorial 5 factorial can't be used. Well, it's because there's gaps in the rectangle, like we said, and not all the arrangements of 4 to the right and 5 down are possible, okay? And that's from those sections that are missing. So 9 factorial, 4 factorial, 5 factorial is a calculation based on that there are no pieces from the grid missing, okay? So because we're missing pieces, not every movement of 9 total movements with 4 to the right and 5 down are possible, okay, because we're missing portions of the grid. All right, so that's the end of that lesson. Okay, stay tuned. I'm going to be doing the next lesson very carefully, but as always, if you guys have any questions or concerns, email me and I'll get back to you and try and help you with those questions. The easiest method is usually, again, as I've mentioned in previous ones and videos, is just to take a screenshot of it, email it to me, then I can usually write on that document and show you some calculations and send it back to you pretty quick. Okay, so have a good night, you guys. We'll talk to you.